Yes, sir. Are there any questions before I go? I put the solutions up on the OneNote if you take a look. Now they're math. Yes, sir.
I don't think I have one. I was the one that took it upstairs. The test.
Did you hand it into the office or me?
I slid it under your door when I was done.
All right. Can you see me afterwards?
Yes, sir.
I think there might be one other person. I honestly don't know if I scored yours. Yes, sir.
Okay.
I do have a question about the project. We are required to do MATLAB.
No, it doesn't have to be MATLAB. I prefer MATLAB for one reason. I have to show that I'm making you use MATLAB. So if you do it there, how can I not say I showed? Yeah.
Okay, and my next question was, is it okay if our homework problem is reference to like a real world situation? Not a real
Yes.
world.
Yes. The problem you create.
But, well, not a real world, but like a world that has no, what's the word?
Like theoretical.
Perfect, a theoretical perfect world.
Yes, the theoretical problem is
Okay.
fine.
Like no errors. Like
Yeah, no errors.
Physics
That's
problem.
fine. That's fine.
Yes,
All
sir.
right. That's fine. What I'm really looking for is I want you to first come up with a problem that you need based on the things that we've learned in this class, using the principles. You're applying principles to some problem, radar, antenna design, something like that. You state the problem in words, right? Then you diagram a solution, right? Basically bullet points. This is a very simple thing. Then you go ahead, this is just like a journal paper. And then the next thing you do is you show how you implement the solution mathematically. And what the results are. Either MATLAB results or something, and then you discuss the results. Are they what you expected or aren't they? And then it's just one of these things where it has to look like there was an element of creativity by you, and then you show how in fact maybe the results don't add up to what you thought in the beginning, but you've learned something. Yes?
Mine mine doesn't have exact answers, so like my homework was like come up with a solution for a customer, and so like there could be a different.
Well, there might be many solutions, but you have to show what you've done, and I need analytics. I need mathematics and then results that are mathematical. All right, here's the equation I use. I use Frisch transmission equation. I assume this efficiency with the antennas, this gain, based on that. You've got to be kind of exact, all right? In this one, they're not looking for a 2-paragraph answer. This is not an essay. They want to see mathematically how you really applied the concepts you've learned mathematically and then came up with a solution. Now, the solutions are up there. We went over them last class. They're up there on MathCAD, so you got to kind of parse through those things. All the problems that I gave you were on homework, were based entirely on homework, to be honest with you. I don't, really wasn't one problem that stood out as a difficult problem. I think everybody, if you made mistakes, they were silly mistakes, in my opinion. And that was the real truth. They weren't, I'm not worried about anybody maybe a couple people who really didn't understand what's going on, but the only one I'd say that caused me a little concern was the last one, were the S parameters, because there were some really kind of bizarre ideas put forward. And if you did the homework, that's a homework problem. I don't know if you realize that. That is a homework problem. Okay? All right. Now, here's the deal. We've got about a week and a half before finals start, roughly. I'd like to see next week, if you don't mind, start getting those projects in. And I want you to send me an email copy where it says project, right? And your name, MATLAB, put E3320 project in your name in the subject line so I can easily cull through these. I honestly don't know how many emails I get a day, but at the end of these 2 classes, I'm probably going to have to go through 100 emails. And most of it I don't really care to. It's not really important. But if I see in the subject line that, I'll pull these out and put them in a folder. That way I can cull through them easily. The second thing is, chapter 10 is the end of what we're going to do. There's nothing, when we get through this, that's it. There's nothing new coming for the final exam. But I am going to go back and probably refresh you before the final on several areas we've discussed. And if you have specific questions regarding any of the material we covered you want me to address in class, then do it. Ask me, and I'll do that. Yes? How many questions? All right. So let me give you the way I make up a final. On all my hour tests, I have 4 distinct problems that have multiple parts. That's the way I make up every hour exam I've ever done here at this university. On the final exam, because it's 2.5 hours, I don't make it 2.5 times as long. I'll make it 6 to 7 problems at most, each of those having multiple parts. Now what I do is cover all the topical areas, antennas, radar. I cover really, propagation in free space, reflection, shielding effectiveness, S parameters, all the things, the major themes. Follow me? And I will cover EMC, that will be on there, but I'm not gonna, something like, when we talk about EMC, if I talked about inductor, resistor, capacitor, if I asked for specific information based on a chart or something like that, and you know what I'm talking about, right? You had a quiz on. What I'm not gonna do is try to ask something that I haven't asked before in great detail. I'm not gonna do that. It's the major themes, and that's the way it always is on a final exam. I will tell you one thing on the final exam, if in your best interest to get as much rest as possible, because you can't afford to make stupid mistakes on a final. You need to be rested, and you shouldn't come in here super sleep deprived, or you're gonna wish you didn't. And this happens, and I'll say the biggest, in my opinion, the biggest, and I haven't done this statistically, but when I've looked at final exam scores over any of the engineering courses, from circuits to 3320 to signals and systems to even EMC and radar, the biggest discrepancy is on the final, because I don't give formula sheets, and I don't give anything that's going to be something you can get points out of cheaply. It's all, if you know it, you're going to know it. And if you don't know, it's really apparent. So on a final exam, I will get lots of hundreds or very high grades, and I'll get lots of people where you get 12s out of 100 kind of deal. Just remember that. If you're smart, get your rest, and don't cram, study for it on a daily basis, and you'll be fine. And that's my best advice to you, because it eliminates the stupid mistakes when you're not cramming and panicking. That's my opinion. I know you have a lot to do. Today I'm going to cover one thing. Yes, sir. I think I covered that. That's going to replace a quiz, right? Didn't I say that? I said that's going to literally be, I'm going to dump your lowest quiz to begin with, but that's going to go in there for the quiz grade. And just do a decent job on it. If you try to just give me crap, I'm not going to give you points. Yeah?
To be clear, we still have to do it even if we don't want to.
If you don't do it, I'll flunk you.
Wait. So you're talking about ABET right now, but he's on our syllabus. 10% of our grade is dedicated to the MATLAB project. And you moved
This is it.
into
This is it.
Okay.
This is it.
So our quiz is worth 30%?
No,
Then what's the grading?
it's a misstatement. It's not going to be that. All right, I'm just telling you that was on there. I should have corrected that earlier. Reason I can't do that in this class, to be really honest with you, I used to give a very complicated MATLAB project. All right? And it would involve designing things. And what I found happened was I'd get groups of people working together. And no matter what I did, I could make it as unique as I want. And it became more like a collective grade. All right? I'm being honest with you. All right? And, there's really nothing you can do to stop that kind of stuff. So what I've decided is I'll give this, all right, and even though it says 10%, I'll adjust for it, all right? So it's going to be this way. First test, 25%, second test, 25%, final, 30%, homework, quizzes, and that, 20%. That's 50 total. That way it's fair. If that MATLAB project, it doomed some people because it was direct copying, and I saw it, 5 people exactly the same thing. And so what do? Take 100 points, divide by 5, they all get 20 out of 100, and they're all mad. No, I'm not going to do that. You know what I'm talking about, because I see the stuff that goes on. It's unbelievable. What I wanted to cover today, now I'm trying to be as fair as I can about this, too. What I'm going to cover today is going to be something, and I know we've had a break, and it's going to be in Chapter 10, it's really circulators. This is S parameter stuff, and I'm going to tell you the application. I'll give you the page number on this. And I'm going to actually talk about the moving the reference plane, too. There's a couple little things. Let me do the reference plane first, then I'll do the circulators. There's a couple things I want to cover, but those are the primary. All right. First, the reference plane moving. This is fairly simple if you pay attention. If you try to cram on this one, you get clobbered. All right. In general, if we have just a two-port network where we have port 1 here and port 2 here, and we assume we have the S-parameter matrix that defines this, all right? Now, what is not said, what I didn't say as before, is port 1 assumes that's the actual reference point for port 1. And it assumes that's the reference point for port 2. Now, I'll get to why I'm saying that in a second. Does everybody follow me on that? So it means that when we have V1 plus coming in and V1 minus coming out and V2 minus coming out and V2 plus coming in, that we can write V1 minus, V2 minus. I'm going to try to get a better marker. Equal to S11, S12, S21, S22 times V1 plus, V2 plus. That's the definition of what's going on with these S parameters with these two ports right here. Now, here's what goes on oftentimes. They'll get the S parameters for this particular thing, but they need the S parameters for something adjusted for distance and things like this, because on a board, you're always going to have links to cable. You're going to have a distance that you have to connect something, an amplifier or whatever. You follow me on this, class? So what they'll do is this. They're going to say, if we had that same S parameter matrix, that's this, and now we have, matter of fact, I'm going to put it up over here. And now I have this, where I have a length of cable. Here's my S matrix, and then I have another length of cable. This length is going to be L1, and this length is L2. This has a phase constant beta. This has phase constant beta. It could be beta 1, beta 2. I'm going to just leave it as beta for now, assuming they're the same. And now I want to move the port from here to here. So now this is my reference port. This is going to be called 1 prime. And I'm going to move this port. This would be 2 prime. So I want the S parameters for this so that when V1 plus now comes in there and V1 minus comes out and V2 plus comes in and V2 minus comes out, I want this, I want the S parameters for this. Do you understand this, class? It assumes you have these S parameters originally. So this is how you adjust for this, and I want you to pay attention. A lot of times electrical engineers where you're at don't see this. That if you just have a line, a transmission line, let's assume it goes on forever, and there's some characteristic impedance, and there's some constant beta, right? Well, if I have a signal right here, I'm just going to call it V1 plus right here, coming in. It could be 10 at an angle of 0 degrees. It could be anything. Remember, we're in a phasor domain, so it's magnitude and phase, right? But it's propagating in that direction. Well, down here, if I go a distance L, then the actual signal here, if there are always no losses, will be V1 right there plus, but it'll be delayed in phase by e to the minus j beta, in this case just L. Now the only thing that does is change the phase. Remember what beta stands for. It's radians per meter, right? A phase change. So if I have 10 at an angle of 0 degrees, and I move down, say, pi radians, that's 180 degrees, correct? Then this would be 10 e to the minus j pi, right, radians times, it's really going to be the beta times L, but if that came out to be pi, it would just be e to the minus j beta pi. It phase delays it by a certain amount. Does everybody follow me on this? Doesn't change the amplitude, just the phase. This is important, just the phase. Now, when you look at this, and we recreate the matrix here, this matrix that's going to be from here to here, defining these S parameters, we'll call it S prime. Now when I look at that, my S prime, and this is in the book, my new matrix will be this, and I'll explain this. Put down S11 first. Now that's the reflection coefficient, it's the ratio of V1 minus to V1 plus, correct? So V1 minus to V1 plus, assuming you're right here. But hear me now. Now when I move back to here, now the signal travels L and then 2L. Follow me? So when I look here, if that's L1, the signal is going to travel L1 and then back to L1. If I talk about V1 minus over V1 plus, does everybody see this, class? So what happens right here, my S11, the original S11, is just going to be multiplied by e to the minus j beta, and it will be 2L1. And that will take care of this phase delay, because now the signal V1 has to move down here, has to hit port 1, and then reflect back. Does everybody follow me on this? It's not hard to see, but you have to be clear about this. Now, when I look at S22 over here, the original S22 is the ratio of reflected to incident signal on port 2, right? Assuming there's no V1 plus coming in. Well, now if it moves back here, the original signal travels first, its phase delay e to the minus j beta L2, and then its phase delay again back when it reflects. So now this is going to have e to the minus j beta, and it's 2L2. Does everybody follow me on this? This really just accounts for the phase delay when you move the ports. And it's almost invariable. It's something you're going to have to deal with when you're doing engineering work. You can't always get things exactly where you want them, so you have to have lines that are called, I call them delay lines, but they affect phase only. Got me on this? Now, what about S21? Well, S21, in case you don't know it, that's what? V2 minus, pardon me, over V1 plus. So it's really what? If I put V1 plus here, it's how much of that signal comes out here is V2 minus. Correct, class? Well, if it's phase delayed, if I add this length and this length, then it's going to be delayed e to the minus j beta L1 here, and then e to the minus j beta L2 there. Does everybody see that? And this will be the same for S12. So this has e to the minus j beta. It's just L1 plus L2. Here it's going to be S12 e to the minus j beta L1 plus L2. This is a very simple concept. The key is knowing what beta is and knowing what the links are. And those will be apparent. There's no way those things are going to be hidden from you. Okay? Does that make sense to everybody, class? It's moving the phase planes. Now, why do you need to do that? Because a lot of times, first, suppose I'm measuring the device, all right? And no matter what I do, I still need to connect by long lines to it. Well, then if I want the actual S parameters of that device, I have to do what? I have to actually eliminate these exponentials from, I have to do an inverse of that. I have to multiply S11 times that by e to the plus j beta 2L1. Do you follow me? To get the actual S parameters. Everybody on me on this? It's just the inverse problem. But this is how you do it if you're adjusting for the actual phase delay by long lines. And that does happen a lot. I don't have a lot of personal experience building amplifiers for high frequency work, but I know that does happen. Is anybody going to take the high frequency analog or design? I think it's RF design that we have. Oh, you are? Is Dye teaching Foster Dye? If he teaches it, he's very good. He does a lot of radar work, and they build very high-frequency amplifiers, and he knows all the things that really are applicable to design, onboard design like this. Because high-frequency amplifiers, most of the time, they're not, you know what Class A amplifiers are? Class A amplifies the entire wave completely without distortion. There's Class AB, right? And that's on the verge of clipping. And then there's all these other classes where you get a lot of clipping and you can, and a lot of distortion. But those are okay as long as you're talking about power amplifiers, not actual signal fidelity. That's another lecture. And you'll see how when you're dealing with a lot of high frequency amplification, you're dealing with Class AB or Class C amplifiers where there's a great deal of clipping and things like that. Just realize that. All right, that's we could do a problem with this, but it's straightforward, most of this stuff right here. The only thing you have to do is get beta and L correct. And usually, even though I'm not sure with Wentworth's book, usually what they're going to have there is something that's in degrees, not radians, unfortunately. I prefer radians, that way everything works perfectly, but you're going to see like e to the minus j 45 degrees or something like that. So when you do his problems, you'll see. The next thing we have to cover are going to be circulators and then four-port systems. And I'm going to explain why circulators are important first. And his book, he does a good job just exposing you to this. These are not hard concepts. The hard concepts are when you try to analyze something that's a three-port system. By the way, when is our last day of class?
Friday.
Not this Friday.
This Friday.
Oh, no. It is this Friday?
Yeah.
Finals next week, late Thanksgiving.
Oh, my goodness.
Finals Wednesday at noon.
All right. I should know this, but I've got other stuff that's all scheduled all over the place. How about we do this? Can you get your projects into me before, not this Wednesday, but the following Wednesday? Everybody? I need them with your name, right? And 3320 project, something like that, so I know I can pull them all out in the folder, because I got to grade these things. And I'd like a turned in piece of paper with it too. Yes? I want both. Both. All right, yeah, hand that in. Can you do me a favor and stick it in that Dropbox outside my office? I'm in 423. Just make sure you do it. Make sure your name's on it legibly. And I'd ask that also, if you're doing MATLAB, put all the figures in there and the actual code you used. All right? All right, thank you. Now, these are circulators, the next thing. These are all multi-port systems. This is a three-port system. Write that down. You can have any number of ports. Those are just entries to incoming and outgoing signals. You can have as many ports as you want. Typically, 4 ports about where you draw the line. So what is a three-port system? Here's basically what it is. It's called a circulator. And this is done, they have materials that actually direct the signal, magnetic materials. I don't have a lot of experience in this. But this is more of a thing that what happens here is a material science kind of problem. It's not done with diodes. What you're going to have here is port 1. This will be port 2. And this will be port 3. Now here's the goal of a typical circulator. If this is V1 and you have V1 plus coming in, they want all that signal to come out port 2. So they want all this to come out V2 minus. Then they want in all the signal incoming here, and port 2, that would be V2 plus, to come out port 3, that would be V3 minus. Do you follow me? It circulates, comes in, it's almost like a roundabout. Comes in, zoom, that way. Everything coming in here would go this way, follow me? Ideally everything, it's not always, it's never everything, it's most of the stuff. And finally, anything coming in here will come out here. So the V3 would be V3 plus coming in, would come out V1 minus, okay? Everybody get the idea on this? And somebody will say, well, can it go that way? Yeah, it could, but I'm talking about this circulator that I created is going to go this way, right? Everything coming in port 1 goes out port 2. Everything coming in port 2 comes out port 3. Everything coming in port 3 comes out port 1. Follow me? Now, first, why is that important? With radar, you have transceivers. You transmit, then you receive signal, right? So if you put up an antenna here, and it transmitted anything, right? That's fine, but what if it received in that port? You would want all that signal come at another port for actually analysis. And I'll show you more of an application. These are standard things that are used in radar when you have transceivers, especially when you have the same horn isn't used for transmission or reception. This is typical. So now, what does the S-parameter matrix look like for this? So let's just take a look at this. We know we're going to have a V2 minus, right, over a V1 plus equal to 1, right? Well, what is that? That's S what? 2, 1, isn't it? Right? 1's going in, 2's coming out. Isn't that right, class? That's S21. What else do we have in? We have V3 minus over V2 plus equal 1, correct? Well, what is that? That's S2's coming in, right? 3's coming out. Correct, class? S32. Do you follow me on this, guys? Make sure you do, because you have to understand the way I'm creating this matrices. This is an ideal matrix. We're saying everything coming in port 1 comes out port 2. Therefore, this ratio is 1 without any phase delay. Second one, V2 plus, anything coming in there comes out V3 minus, right? That would be 3, 2, right? And then last, we're going to have V1 minus over V3 plus equal 1. So that's going to be S what? 1, 3. Do you agree with me, everyone? And this is an odd-looking matrix. And I'll give you a problem I can ask you, a theoretical. So what does the S matrix look like for this? Well, when I look at this, I've got S21 is 1. That's here. Then I have S32 is 1 also. That's here. And then I have S13 is 1. That's here. That means this is 0, that's 0, that's 0, that's 0. Down here. That's 0, and that's 0. You all see this? Now, does anybody have the book with you? Take a look in his book on Circulator. So he's going to show you the S parameter matrix, maybe on the next page.
It's right here.
Oh, is it? And take a look at that. He's got a 1, he's got 3 1s, the rest zeros, right?
Right.
Now, that's really not true. That's the ideal world. It's not the real world. What happens is this. These will have values. They may be 10 to the minus third, 10 to the minus fourth, 10 to the minus fifth, all right? There's some degree of coupling that's inevitable. You can't get away from it. So what they'll do is they'll say there's a certain amount of isolation between the ports. And if you want the isolation between port, for instance, between port forward now, between 1 and 3 going this way, you would have a port isolation, and it would be S, if you think about that, that would be S31, right? S31, if it came in 1, came out 3. And they would say the way they do it is take 20 times the log of, I'll just put just, let me write this down. Suppose I have S31. That's how much comes out port 3 that came in port 1. Do you all follow me on this, class? And they'll have something like 10 to the minus 6. Oh, maybe not that. Maybe 10 to the minus third. So that's a voltage ratio. Do you follow me? So they want the port isolation. Well, when they talk about port isolation, and this is true for anything really, any kind of port isolation, they will say that there's going to be, and I call it, in his book, he's going to use different terminology, but it's port isolation. He uses insertion loss and then isolation, but really almost all these in the real world are called isolation losses, and they define it as like the isolation loss, and it's always the port number. So the S31 would be the isolation loss on 3, 1. All right, follow me? Coming in 1, coming out 3. And it's 20 times, it's actually minus 20 times the log of, and in this case it would be 10 to the minus 3. Follow me? Now, if you look at this, remember it's voltage, so it's 20 log. The minus sign is just put there so it'll give us a positive value. It's the level of isolation. Well, the log of 10, log base 10 of 10 to the third, minus third is minus 3 times 20. Minus 20 is going to be 60 dB of isolation. You follow me on this, class? All the other problems in his book regarding that in the examples, he'll say there's, for a 4-port, you're going to get something called isolation loss. Then there's going to be the insertion loss, the S21. But always when I ask this question, it will be relevant to the port it enters and the port it comes out. Follow me, class? That will be it. So if that was the case here, if that S31 is 10 to the minus third, well, that would be here, right? Right here would be 10 to the minus third. Correct, class? So if I give you a matrix with different things here, and I ask you for the isolation in certain ports, you could do that. Do y'all follow me? The other thing is this. The way I showed you, this is a system where 1 goes to 2, 2 goes to 3, 3 goes to 1. It doesn't have to go that way. I might ask you to create the matrix for this. This is just a 3-port. Suppose I said now, all of port 1 goes into port 3. All right, everything that comes in port 3 comes out port 2, and everything coming in port 2 comes out port 1. Follow me? Exact same problem, right? But instead of going clockwise, it's counterclockwise. Does this make sense to everybody? Now that one's pretty straightforward. Most of you can see it. Here, I have port 1 to 3 coming out, right? So it'd be S31, right, would be 1. Do y'all follow me in this class? How many see what I'm doing here? And that's the whole thing with this all these things that are circulators and things like this. They're mainly used to really, if you're using, if you're having things where you want signals separated, suppose I've got an antenna here, right? And I want all the signal coming this way that's being received to go to some kind of digital processing thing, but I want all the signal coming this way to actually go to the actual device. Do you follow me on this, class? Well, with a circulator, you can do that fairly straightforward because now you would have the feed on that antenna, say coming out port 2, if it was being fed from port 1, and then everything coming back on that antenna, you'd shunt out port 3 for processing. Do you all follow me? And that's sort of typically done that way, and it doesn't require any switch. There is no transmit-receive switch for something like this if you're using a single antenna. Does that make sense to everybody without going into all the details? How many understand that right there? All right. It's not, I'm not trying to make this hard. There's a lot of applications. This is one of them. For digital signal processing, there's innumerable numbers of applications where you get all these streams of data, and you want to make sure that data coming one way is going to be processed a certain way, data coming the other way is processed a different way, and that's what they use circulators for. But you can look up some of this stuff. And they do a pretty good job. In his book, it's very simple kind of thing, but he talks about the applications. Now, there are also 4 ports. He calls them couplers. This is just more of the same. And you can have any number of ports here. Now, Dr. Wentworth probably could give you a lot more background on why this is so important to have this isolation port. But normally what happens is this. With microwave, what you want to do is you want the power to get to a device or an antenna. So you're going to have something like an S21. What comes out port 2 from port 1? You'd like that to be 1. 20 times the log of 1 is 0. You'd like 0 dBs of attenuation or isolation there. But then you want some isolation on another port, but you also need a reference signal. Now let me explain something. With radar, you transmit a signal, but you need some of that signal. You're going to use some of that signal to do digital signal processing, and you'd like the signal to be synced with the exact time it was transmitted. So they peel off some of it. All right. Then there's another port, and this is the one that has the greatest isolation. What that port's used for is beyond me. I've never used it, but it is used. People do use it. I'm trying to tell you, that's a 4-port system. So anyway, with 4-port systems, I don't ask much about this. He's going to have port 1 here, right? And then he'll have port 2 here. And then he'll have port 3 here. This is called the isolation. And then he'll have port 4 here. And he's going to, in his book, the way he does this, oh, I'm sorry. He's drawn it upside down. He's got port 1 in the bottom. But I can do it his way. He's got this drawn 1, 2, 3, 4. Now, don't get hung up about the port designations if this is upside down or this way. Here's what he's going to have. This is the through port. S21 dictates that, and you would like that ideally to be 1. All right, that's what you'd like. Follow me on this, class? Now, there's a thing called a coupled port, too. He uses the word coupled. All right, and that's port 3. That's where you peel off some of the signal at the same time. It's going to be linked to an antenna for transmission. And that port right there will be used for signal processing information. Yeah. Well, I'm not sure it's a page, but 571 has a picture of it at the very bottom. If you look at pipe, it's just a 4-port system. Remember, you can get as many ports as you want. It doesn't matter. I'm just giving you an overview. It's called the coupled port. This will be maybe 10 to the -2 type stuff. And then there's the isolation port. He uses I there. But again, the designations you worry about is you want to look at S, like for this, coupled is S21. Follow me? This is S31, right? This is S41. And in S41, it's very high attenuation. Why you use that, I don't know. I don't ever use that. Anytime I'm doing one of these things, if I don't need anything out, I'll just short it out. But if you look in there, you're going to see he talks about this. Now, mainly what you have to understand is when you're doing very high frequency engineering work and stuff, you always want the signal, the exact signature of the signal at the time it's sent. And that's why this coupled port becomes important, because that'll be exact replica of this, only orders of magnitude less. And that way you can do digital signal processing work. With that, you know what a match filter is? You can take this, you can digitize it, then use that, inverse it, and use it for match filtering the signal coming back, and that way you get the exact range. That's beyond this course, but that's what that port's really used for that. When they get more than 3 ports, all that amounts to is they've got several different things going on. They may have 2 radar signals at different frequencies, all coming online. And by the way, most of the time you have to understand something. When you're dealing with real device manufacturing and you're putting it in like a cruise missile or something, real estate is very, very expensive. I'm by no means an expert at doing any high-frequency amplifier design or power amplifier design for radar. But I know something about it, and I know the big thing you always worry about, because I had a personal problem with this. I think I shared with you the antenna device disaster when, didn't I tell you about the antenna I designed? I had Ball Aerospace antenna design. It was done perfectly according to the program I was using for no, the reflection coefficient 0, standing wave ratio was going to be just 1. It was perfect, right? Well, and then that kid put a solder ball on it. And now my standing wave ratio is 4. Well, it's because I was gigahertz frequency. This is 1.4 something gigahertz. If that would have been 50 or 60 megahertz, you wouldn't have noticed anything probably. So in high frequency engineering, it becomes important to be very precise with lead length and all that other stuff. But when you're doing high frequency analysis and engineering work, especially when you're doing port design, you have to start somewhere and get an idea. You build this and you see if it works. And the big thing is impedance matching. Hear me now. You want to impedance match the circuitry or everything goes sideways in a hurry. And also things blow up if it's a power amplifier. They will smoke. So the first thing they do if they're talking about a 3-port system is they say, suppose I have 3 ports, and this has characteristic impedance Z0. Here's another port. I want characteristic impedance Z0. This is a splitter, by the way. This is a very inefficient splitter. I want characteristic impedance Z0. The whole design hinges on one thing. I'm literally showing you in terms of like, these are 2 wires separating so you can see what goes on. What they want to make sure is this happens. If the impedance looking into all these things looks the same. Follow me? So what they're going to do is they're going to put a simple resistor here, And the resistor is going to have a value of 1/3 Z0 here. Then they're going to put a resistor here of 1/3 Z0 here. Now, bear with me. This is not a good drawing, but you've all followed me. Now, here's the deal with the signal. Call this port 1. The signal's coming in. It's V1 plus. That's port 2. Some of the signal's coming out. That's V2 minus. But the same amount of signal will come out of here if this is port 3. And that will be V3 minus. Do you all see what's going on here? It's splitting the signal ideally. The problem with this design, and I'm going to show you its impedance match, is you're losing power here and here. You follow me on that? That's 1/3 of an ohm, that's 1/3 of an ohm. These are very short lead links, so you don't have to worry about that being a transmission line in there. And this is just taking that and grounding that, taking that and grounding that to there. Now, what's the input impedance looking in port 1? So what is Z in looking in port 1? Well, think about the way this actually looks. I've got Z0 here, right? And then I have Z0 over 3, and then I have Z0, if you think about it. Over here, I have Z0 over 3, and then I have Z0, right? Now, this looks like 4/3 Z0, doesn't it? And this looks like 4/3 Z0, correct? I think that does it. I think he shows this in his book, but I'm just checking to see if he does it. Oh. My bad. I did one thing wrong. And I'm sorry. I'm going to have to draw this up quick. I forgot the central hub point here. That's going to be Z0 over 3. This is Z0 over 3. This is Z0 over 3. It's in his book. This coming back here is Z0. This coming out here is Z0. And this coming out here is Z0. I'm sorry about that, but I forgot the central hub right here. Now, that's what I meant to show you. So when I do this, here's what I should say. Looking this way, does everybody see that's 4/3 Z0? Looking that way, you have Z0 over 3 plus Z0. Here, looking this way, it also looks like 4/3 Z0. Do you all agree with that? So 4/3 Z0, 4/3 Z0 means the parallel combination is 2/3 Z0. Do you all follow me in that class? Then when you add the Z0 over 3, you get Z0. So in fact, here looking in, it's Z0. This is one way to get no reflections. That will do it, but now you're losing all this power here and here. So you're losing a lot of power. And now your S21 is not 1, it's greatly reduced. Do you all follow me in this class? Even if we did a power split without these, it would still be a problem with impedance matching. You get an even worse problem. But that's the reason this is bad. So the next generation, something I'm going to cover next time, it's called a Wilkinson divider. And that uses transmission lines. This is on the top of page 571. Let me just finish with this. This is going in the right direction of giving a higher efficiency, all right? Problem with the Wilkinson divider, it only works at 1 frequency. It has to be built for 1. That works for any frequency. This is limited to 1 frequency or the whole thing goes fluey. And it's based on a quarter wavelength design that I'll talk about. After that, they get into things called really active couplers and stuff like this that are much more expensive. And they will work over a band of frequencies, but again, because they're active, they're consuming power. And they're also larger and more expensive. I'm going to cover that. We'll finish this up tomorrow, or next lecture. And if you got specific questions, come see me.